Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 22. The topic for lecture number 22 is vapor absorption refrigeration system. Before getting into the contents of this lecture, let's recollect what we have discussed in the previous session. So, in lecture number 21, in lecture number 20, we started with the working principle of a vapor compression cycle. Then in the previous lecture, we saw the methods to improve the enhance the coefficient of performance of the ideal vapor compression refrigeration cycle. The COP is the ratio of the desired effect, or which is the refrigerating effect, amount of cooling produced to the work done on the compressor, that is power required to drive the compressor. So, if you want to increase the COP of the system, either the refrigerating effect have to be increased, which is the numerator term, or the denominator term, which is the power required to drive the compressor, that has to be reduced. So, there were three methods which were employed. The first one is subcooling, that is cooling the refrigerant below the saturated condition. So, we solved one problem in which the degree of subcooling was 6 degrees centigrade. The condenser temperature was 32. So, when we have a degree of subcooling of 6 degree, the temperature after the temperature of the liquid refrigerant after subcooling is 32 minus 6, that is 26 degrees centigrade. We saw the enhancement in the COP of the system in this method. Next, we have seen the superheating. So, what happens is when the refrigerant vapor comes out of the evaporator, which is a low pressure, low temperature refrigerant vapor, before it reaches the compressor, it is slightly superheated due to the heat transfer and all. So, before the actual compression, the condition of the refrigerant at state point 1, it is in superheated condition. So, in the previous case, it is assumed to be a dry saturated condition. So, after isentropic compression, the refrigerant state changes from saturated to superheated region. Whereas, in the superheating method, already the condition of the refrigerant, it is slightly superheated, and further compression increases the pressure and temperature, obviously, like any other compression process. And so, in this method, both the before compression state and after compression state, the condition of refrigerant is superheated. Then we have seen the combination of these two methods, that is subcooling and superheating, subcooling and superheating. We have compared the COP of the system of these methods with the conventional one, that is the conventional ideal vapor compression cycle without subcooling and without superheating. Now, let us move to the contents of this lecture. Introduction about the vapor absorption system, refrigeration system or cooling system, properties of the working fluids. So, primarily we will be discussing about two systems, ammonia water absorption system and water lithium bromide absorption system. So, if you look at the schematic, so this is primarily, I have shown a grid portion is shown. So, this is the fossil fuel which is primarily burnt in the power plant. So, the heat of the fuel is used to convert the water into steam, generate steam in the boiler. Then the steam, before it is expanded in the turbine, its velocity is increased in the nozzle, then expansion in the nozzle, then condensation, then after condensation, the feed water is pumped back to the boiler by a feed water pump. So, that we have seen in the ideal Rankine cycle. So, here the conversion of the fuel heat supplied to the boiler is converted into the power by generating steam and expanding in the turbine. Now, this power only is used to drive the compressor. So, the power required to drive the compressor, it is not generated or produced in the place where we are using it. All of us are familiar that the power plants are located far from the end user. So, it is not near to our home or near to our working place or the institution where we are employed also. So, there are different types of losses which takes place. After the power is produced, by the time it reaches the end user, there is a transmission and distribution loss, that is called TND loss. End equipment loss is there. So, of course, there are losses in the power plant also. So, finally, if you see the efficiency, it is very, very less. And the power which is produced in the power plant is used to drive the compressor, is used to operate not only the air conditioning system, all the other systems, be it any electrical device. For those devices, the power requirement is not met from the source which is very near to the end user. So, I am using the power from the grid connected power to operate my compressor and then produce the cooling. So, this is what it is a very simple schematic, and it is, in fact, it is a self explanatory one also. Now, if you look at the numbers in this slide, so most of the power plant we have the efficiency is not more than 30%, or very few cases will have 35%. Okay, so, I have taken the power plant efficiency at 30%. Here I have done a small calculation. So, that means the remaining 70%, efficiency is only 30%, the remaining 70% is in the form of loss, various heat losses. This is a generator loss 5%. As I said little ago, transmission and distribution loss is there when we transmit the power from the source to the end user. So, that is, and of course, end equipment loss is also there. Suppose this is one example, this is not this one, this is an example. Okay, so let me write example. Suppose my fuel has a capacity to generate 25 kilowatt of power. This is just for making the students to understand. I have taken 25, we can take any number. So, 25 kilowatt is the potential of the fuel to generate power if the efficiency is 100%. If all the heat input is converted into useful work, that means the efficiency of the system is 100%, that means there are no losses, which will not be the case in reality. Okay. Suppose if I have this much potential, so we can calculate all this, apply all these formulas, this losses, various losses. So, this is the potential input, the potential of the fuel to generate, but the actual power by the time it reaches the end user, this value is not at the power plant. This is after the various losses, like after power plant loss, generator loss, transmission and distribution loss, end equipment loss, everything. Okay. So, input is, there is a potential to develop 25 kilowatt of power, but I am getting only 4.25 kilowatt of power. Even if you take this number as 5, it is just 1/5, 20%. So, why I have mentioned these numbers are, so this is the reality. So, when the power is used, when we use the grid power to operate the compressor in a vapor compression system, so it is not even, we do not get even the efficiency as 30%. 30% is the efficiency of the power plant. So, by the time that power reaches the end user through the distribution, transmission and distribution system, and in between there are losses in the generator loss is also there, TND loss is there of course, and also there will be loss at the end equipment. So, if we incorporate all these values, so the actual power output for an input of 25 kilowatt is 4.25 kilowatt. So, if you divide this number, okay, so this is 4.25 divided by 25. So, it will come roughly 0.17 or 17%. So, this factor I am calling it as, this is my source, okay. This is at the site, this is at the site. So, source to site factor. Okay, so what is the source? It is like for to make the students understand, I am just defining one factor, that is called the factor from the source to converting that heat into power, source heat to site power factor. Okay. So, it is just only 17%, it is not even 20%. Now, why I am telling this one? So, this is the power that is used to drive the various devices. It is not available easily, it is not available at a higher efficiency. So, it is not even 30%, it is much less by the time it reaches the end user. And of course, we have to use this electrical energy, which is the high grade energy, to operate the compressor. So, and not only this one, to produce this power, a lot of fossil fuels are burnt, either the coal or this one solid fuel or liquid fuel. So, which are not environment friendly, not at all environment friendly. They contribute to various environmental issues, and also these fossil fuels are depleting substances. It is not a renewable source of energy. And that is why a lot of attention is paid for the renewable sources of energy like solar, wind, biomass, etc. So, that is not the focus of the present lecture, but still for information I just would like to share this one. Now, for an input of say 25 kilowatt, we are getting an output of little over 4 kilowatt, which is the percentage is very small. It is not even a reasonable number. But of course, there is no other option. If you want to run the compressor, we have to use the high grade energy only. There is no other option. However, in order to overcome these drawbacks, the refrigerants, and also one more thing, the refrigerants which are employed in the vapor compression refrigerant systems are all not eco-friendly. Earlier they were some refrigerants contribute to ODP, some refrigerants contribute to GWP, some of them have contribute to both ODP and GWP. Of course, there are a few refrigerants, a few category of refrigerants that have been phased out or in the phasing out stage. So, which we will be discussing in the next lecture, that is the refrigerants and its properties. So, but if you see the working fluid, that is the refrigerant which is used in a vapor compression system or a refrigeration system or an air conditioning system, it is not environment friendly refrigerant. So, they contribute to ODP and GWP, ozone depleting potential and global warming potential. So, already if you see the source heat to site power factor, it is very less for these type of systems, because we rely on the electrical energy. Okay. And second thing is the working fluid which are employed in this system, in this refrigeration system, this vapor compression system, they contribute to ozone depleting potential and global warming potential. Of course, the COP of these systems are high. We have got systems even COP up to 8, 9. The average COP it's in the range about say 3 to 4 or 4 to 5 in that range. So, the performance wise there is no doubt. Of course, from the viewpoint of environment, most of the refrigerants which are used are polluting the environment. So, either they contribute to ODP or GWP or both. So, what is the alternative for this system? So, the alternative is vapor absorption system which does not use a compressor. Vapor absorption system which does not use the compressor. It is also a refrigeration system or an air conditioning system which produces cooling with a heat source. So, this is very important. It produces cooling with a heat source. Doesn't mean that it does not require electrical energy at all. It requires very little amount of electrical energy to operate a pump. The pump is called a solution pump, which I will explain in the working principle of the system in the next slide, in the subsequent slide. So, this absorption system does not require electricity except to some smaller extent, to a smaller magnitude. And as far as the working fluids are concerned, it employs two types of working fluids. One is water lithium bromide and another one is ammonia water. Okay. In water lithium bromide system, water is the refrigerant, and in ammonia water system, ammonia is the refrigerant. In our country, whenever we represent the working fluid of an absorption system, first we write the refrigerant, the second component is the absorbent, ABSO or BENT. Because in vapor absorption system, the working fluid is a mixture of two, a refrigerant and an absorbent, and it is not like a vapor compression system. Vapor compression system, if you take CFC refrigerant or HCFC or HFC, they are all single component. Of course, if you use azeotropic mixture or zeotropic mixture, there we have two or more refrigerants. But if we take hydrocarbon refrigerant belonging to hydrocarbon category, or CFC, chlorofluorocarbon, or HCFC or hydrofluorocarbon, so these most of the refrigerants, they have single component only. Okay. So when I say water lithium bromide, water is the refrigerant, lithium bromide is the absorbent. When I say ammonia water, ammonia is the refrigerant and water is the absorbent. This is called high resource efficiency. What do you mean by resource efficiency? This the factor which I defined. Suppose let us take a vapor compression system, which has a COP of 5, COP of 5. That is the site COP, That COP is calculated without considering the fact that the power is not produced near to that air conditioning system or refrigeration system. I am not bothered where the power is produced. Power is produced in the power plant, which is very far from the end user, So I am not incorporating this 17% source heat to site power factor. If I incorporate this value into the site COP, in the example which I have told, I have taken a system with COP of 5, vapor compression system which has a COP of 5. So if I introduce this factor, the COP, multiply that 5 by 0.17, which is 17%, it will be close to 1 only. It will be less than 1, maybe 0.8 or 0.9, because it is not even 20%. So even if we take 20% of 5 is 1. So the COP reduces from 5 to 1 if I introduce this factor. So this efficiency or this COP I refer to as resource COP or resource efficiency. So, but this is for a vapor compressor system, when we take the actual site COP, compare the site COP with the resource COP, the 5 COP is site COP 5 becomes multiplied by 0.17, so it becomes close to 1. And if the site COP is say 10 for example, so the actual when you multiply by 0.17, the reserve COP becomes 1.7, close to 2. So it gets reduced by, it is only 1/5, it gets reduced by 4/5. Whereas in case of an absorption system, because the system does not uses electrical energy except to operate the pump, solution pump, and the auxiliary devices like if the condenser and absorber are air cooled, power is required to operate that fan, or if it is water cooled, then that pump for cooling water pump and all will consume little amount of power. But if you compare the power consumed by a pump, by these pumps and fan in the absorption system with the power required to drive the compressor, the power required to drive the compressor is very, very high. Okay. Normally these water lithium bromide systems are used for air conditioning applications, because water is the refrigerant. So the freezing point of water is 0 degree centigrade. So we cannot use water below this one for sub-zero or low temperature applications, that is negative temperature applications. So it is used for air conditioning. Of course, if you add some brine to this one, the freezing point reduces. So that is what is done in the chilled water system. But if you use water as such, we cannot use, it is not recommended to use below 3 degree or 2 degree, because it reaches the freezing point. In case of ammonia water system mostly is used for cold storage applications, dairy, for food processing. Its freezing point is minus 77.7. So, we can use up to minus 75 degrees centigrade. So, the range even if you go if you see the range on the below 0 degree, that is on the for the low temperature application, it can be used up to minus 70 or minus 75. And the capacity of these systems which are available is right from 3 tons of refrigeration to 5000 tons of refrigeration. There are some basic terms which you should be familiar, which are not used in case of vapor compression system. The first one is called a solution. What do you mean by a solution? Solution is a combination of refrigerant and absorbent. So, it is a mixture of refrigerant and absorbent. So, I would be explaining in detail about with an example like ammonia and ammonia refrigerant and water absorbent, and also in detail about the working of a ammonia water system. There is thin difference between ammonia water and water lithium bromide system in terms of construction, which I will tell when I am explaining the water lithium bromide system. Now, we are clear with the term solution. It is a combination of refrigerant and absorbent. Then there are two types of solution. One is strong solution, another one is weak solution. Strong solution is a solution which is strong in refrigerant. If a solution is strong in refrigerant, that means it will be weak in absorbent. We cannot, a solution cannot be strong in both refrigerant and absorbent. It can be strong in either one only. If it is strong in refrigerant, it will be weak in absorbent. If it is weak in refrigerant, it will be strong in absorbent. Okay. So, strong solution means strong in refrigerant and weak in absorbent. Weak solution means weak in refrigerant. So, obviously, it will be strong in absorbent. So, these two are these terms which are, because these terms will be used when we see the construction and the working principle of the ammonia water absorption system, and also these terms are used in water lithium bromide system also. We do not use this term solution in vapor compression system, we say only refrigerant or the working fluid. So, here it is working fluid pair, a combination of refrigerant and absorbent. So, before seeing the construction and working principle of an ammonia water absorption system, let us see the properties based on which the refrigerant, the absorbent and the solution are selected. So, anyway, the next lecture is properties of refrigerant. We will be seeing in detail about each and every property which is required, on what basis the refrigerant is selected. So, if you see the high latent heat, so I have compared this property for both the working fluids. Here water is the refrigerant, so ammonia is the absorbent. Ammonia is the refrigerant in this one, water is the refrigerant. Lithium bromide is the absorbent in the water lithium bromide system, water is the absorbent in case of ammonia water absorption system. Okay. So, latent heat should be generally high. So, this is excellent for water, and ammonia has also good latent heat. Moderate vapor rate pressure, but this is for water it is low, it is too high. Freezing temperature, of course, limited to 5 degree or not below 3 degree. Due to its freezing point at 0 degree centigrade, we cannot use the water. Ammonia freezing point is minus 77.7. So, as I said, you can use up to minus 72 or minus 73. Even if we have for delta T of 5 degree difference, we can use up to very well minus 70 or minus 72.7. Then viscosity, both has viscosity should be low. Then when it comes to absorbent, again the vapor pressure, here the absorbent is lithium bromide, here the absorbent is lithium bromide in case of water lithium bromide system. So, it is called excellent vapor pressure, and in case of ammonia water system, already the water vapor pressure is too low or poor. Viscosity, of course, both has got the viscosity which is required. Next one is solution. Solution means it is a mixture of refrigerant and absorbent, So, first property should be good solubility. So, there's problem associated with the lithium bromide. Lithium bromide, it is available in the form of salt. So when it is mixed with the refrigerant water, so beyond a particular concentration, the crystals starts to form like crystallization. So there is no problem if we use that one up to a concentration say 50 to 55% or whatever it is, but at very higher concentrations the crystallization forms. So the systems would be designed and would be operated in such a way that the crystallization limit is not reached. Solubility, water and ammonia, that is very good. Toxicity, of course water is not a toxic, this one, ammonia is a toxic substance. Low freezing temperature, this is limited to 5 degrees centigrade. Of course ammonia freezing is minus 77.7 degrees centigrade. So it can be used for very low temperature applications up to minus 70 degrees centigrade at least. This is a very important property which is required when we select the absorbent for a particular refrigerant. The absorbent selected should have very good affinity for the refrigerant. Affinity between refrigerant and absorbent, both lithium bromide has got very good affinity for the refrigerant water. Okay, let me underline. So whatever the chemical formula which I have underlined, that is the refrigerant. Okay. So lithium bromide has got very good affinity towards the refrigerant water, and water has got very good affinity towards the refrigerant ammonia. So this is the schematic of a ammonia water absorption system. Okay. So if you see this, there are quite few heat exchangers involved. I will explain each and everything. If you see the common devices, when we compare this, the schematic with the vapor compression system, here C refers the condenser, the same term, EV is expansion valve and E is evaporator. These three components are same. So there is no change. The condenser is present in the compression system, expansion device is present in the, it could be a capillary tube or a valve, it is present in the compression system, and of course evaporator. You will not find the component compressor here. Okay. So the compressor is replaced by a set of heat exchangers. Okay. So let me write it. So in vapor compression system, let me write it VCR. VCR is vapor compression system and VAR is vapor absorption system. So here I have condenser, here also I have condenser, expansion valve or expansion device, here also I have expansion valve, evaporator, here also I have evaporator. Now in vapor compression system, the fourth major component is, I am listing out only the major components. We have got compressor. Okay, so this is not there in absorption system. So this is replaced by absorber, generator, solution heat exchanger, these are all the heat exchangers which are used. Of course, rectifier is used in case of ammonia water only. This is used only for ammonia water system. This is only for ammonia water system. Only for ammonia water system. This device is not required in case of a water lithium bromide system. And we have got another pump, that is called solution pump and pressure reducing valve. This expansion valve is on the refrigerant side. This pressure reducing valve is on the solution side, solution circuit. pressure reducing. So, these devices replace compressor. So, that is what I have mentioned here. A is the absorber, then solution heat exchanger, generator. Okay, so this is not an electrical generator, this is a generator used to generate refrigerant vapor, and absorber is the device which is used to which absorbs the refrigerant vapor. I will explain the process. SHX refers to solution heat exchanger. So, this is solution heat exchanger SHX. This is absorber is A, condenser is C, okay. Condenser is C, expansion valve is EV. So, let me write whatever the letter I have used in the schematic, I am writing it so that when you refer it will be easy. Due to space constraint, so I have not given the legends for these letters, so which I am giving in the next slide. And this is evaporator, and of course compressor, because I am using letter C for condenser, CO refers to compressor. This is in case of vapor compression system. And absorber, G is generator, SH is solution heat exchanger, rectifier is RE, otherwise you can have R also, solution pump is SP, and pressure reducing valve is PRV. Let me explain the process. So, I have given in case of vapor compression system there are only 4 state points: outlet of compressor, outlet of evaporator, outlet of condenser, and outlet of expansion device in case of an ideal case. So, here there are total, if you see the components 1, 2, 3, 4, 5, 6, 7, 8, 9 components are there. 1, 2, 3, okay, 1, 2, 3, 4, 5, 6 is called solution circuit, okay. 1 to 2, 2 to 3, 3 to 4, 4 to 5, 4 to 6, it is called solution circuit. Solution circuit. In this, if you take 1 to 2, 2 to 3, it is strong solution circuit. Strong solutions. I have used a continuous line. You can see here the continuous line represents strong solution, the dashed lines represent a weak solution, the continuous line and a dot line represents the refrigerant. So, this is the refrigerant circuit, okay. This is the refrigerant circuit. Let me edit it here. So, this long line and short line, this forms from 9, 10, 11, 12, this is the refrigerant circuit, okay. Of course, 7 is also refrigerant circuit. So, strong solution, 4 to 5 to 5 to 6 weak solution, okay. So, in this is strong solution and this is weak solution, and the refrigerant circuit is 7, 9, 10, 11, 12, okay. Of course, refrigerant circuit, this is refrigerant, okay. REFRIGERANT. Now, let us explain. So, the strong solution, this is also a 2 pressure system like a vapor compression system, evaporator at low pressure, condenser at high pressure. So, here also low pressure evaporator, the evaporator pressure and absorber pressure are same, absorber is A, high pressure is condenser and generator. So, if you see absorber pressure will be equal to evaporator pressure, generator pressure will be equal to condenser pressure. So, it is a 2 pressure system only. In this case, the rectifier will be also at higher pressure only. So, these 3 are at higher pressure, these 2 are lower pressure, and there is a expansion device which separates the high pressure region and the low pressure region, okay. So, there is no change on the left hand side. This is similar to the 10, 11, 12, it is similar to the vapor compression system. Vapor compression system. The arrangements are similar to vapor compression system. So now strong solution is pumped. Because absorber is at low pressure, generator is high pressure. You know, all of us know that the liquid cannot flow from low pressure to high pressure without using an external device. So the device which is used is the solution pump. Why it is called solution pump? It is used to pump the solution. What kind of solution? Strong solution. So 1, 2, 3 is strong solution, 4, 5, 6 is weak solution. So the strong solution is pumped from the absorber, not directly to the generator. It is pumped by pump through a solution heat exchanger. Why this solution heat exchanger is used? This solution heat exchanger is used to preheat the pumping strong solution. The strong solution is preheated in the solution heat exchanger before it is heated further by the external heat input in the generator. So 1, 2, 3, if you see there is one term, one more term is there. If you take the vapor compression system, if you want to find out the enthalpy, if you know the temperature, we can find out. If you know so there we have only pressure, temperature, enthalpy. Here there is one term called concentration. Concentration, which is represented by the letter capital X. The other name for concentration is mass fraction. Mass fraction. Okay. So concentration or mass fraction. Mass fraction. So this is there for both strong solution and weak solution. Okay. So XSS means concentration of strong solution. Concentration of strong solution. Okay. Let us take a value of 0.35 or 35%. Okay, 35% or 0.35. Okay, we will take in terms of this one. Okay, let us take 0.35. XWS is the concentration of weak solution. When I say strong solution, refrigerant quantity is more compared to weak solution. When I say weak solution, the refrigerant quantity is less. So if you see, remember this slide, strong solution is strong in refrigerant, weak solution is weak in refrigerant. So let us take 0.25. When I say strong solution concentration is 0.35, that means it contains 35% ammonia, remaining 65% water. Again, if you see 65 is a larger number than 35, how I am defining this as strong solution? Before explaining, let us write the similar numbers for the weak solution. When I say weak solution concentration is 0.25, the solution contains 25% ammonia, 75% water. So here the comparison should not be made horizontally, it should be made vertically between strong solution and weak solution. In strong solution, the ammonia quantity is 35%, whereas in weak solution it is only 25%. So 35 is a larger number than 25. So I am defining the solution which has more refrigerant compared to the refrigerant quantity in the other solution. So we should not compare horizontally, the comparison should be like vertical. So if you compare this one, okay, so it is 35%. Similarly, if you take absorbent, strong solution contains, what is the definition for strong solution? Weak in absorbent. If it is weak solution, strong in absorbent. That means in the strong solution, the absorbent quantity for the example which I have taken, for the concentration which I have taken is 65% water. But if you take the weak solution, the water amount is 75%. So the comparison should be made like this. Okay. And again, how to find this value? There are charts or the equations, empirical relations available. Just I quickly will tell.
strong solution concentration is a function of, let me put equal to sign, it is a function of, strong solution concentration is a function of absorber pressure and absorber temperature. Weak solution concentration is a function of generator pressure and generator temperature. Again, what is absorber pressure? Absorber pressure is nothing but evaporator pressure. Here I have written absorber pressure is equal to absorber and evaporator operate at same pressure. So, this is function of absorber pressure and evaporator pressure and absorber temperature, and this is a function of generator pressure is equal to condenser pressure. Generator pressure is equal to condenser pressure, absorber pressure is equal to evaporator pressure. So, condenser pressure and generator temperature. Okay. So, there are charts available, PTX chart, pressure temperature concentration chart. So, using that chart we can find out the value PTX. P is pressure, T is temperature. If you know pressure and temperature, you can find concentration, or if you know temperature and pressure and concentration, we can find out the temperature. Okay. If you know any two property, we can find the third property. So, using this chart, okay, and there are empirical relations, empirical relations also, empirical relations from the published literature. Okay. Now, the strong solution is pumped, it is this one. Now, what is the source of heat for the strong solution? The strong solution is heated by the returning weak solution. How the returning weak solution can heat is the solution returning the generator and the solution leaving the absorber for the in the thermodynamic analysis, we assume it is saturated. Similarly, the refrigerant leaving the condenser, okay, and the refrigerant leaving the evaporator and condenser are saturated. Here it is liquid, here it is vapor. Now, this strong solution at point number 2, it is heated by the returning weak solution. The returning weak solution has got lot of heat. T4 will be equal to Tg. If the generator temperature is 100, T4 will be 100. And absorber and condenser mostly it will be same temperature. Let us take this is absorber at 35, condenser at 35. Absorber at 35 means after pumping the temperature may not increase that much, marginal change, and but the pressure of the solution is raised. So, it is entering here. For example, if you take 35 degree, T2 is 35, here T4 I have got 100 degree. The generator temperature, there is a formula to calculate what is the minimum generator temperature required if we know evaporator temperature, absorber temperature and condenser temperature. Okay. So, if this is 100 and generator is the highest in the maximum temperature, the highest temperature is the heat exchanger which is operated at the highest temperature is the generator. Next is the absorber and condenser, and evaporator is the lowest temperature. So, if T4 is 100, T2 is say 35 degree or 40 degree. So, I use a solution heat exchanger. The returning weak solution is cooled, the pumped strong solution is heated. If I do not use a solution heat exchanger, T2 will be equal to T3, then I have to provide more amount of heat. You see the COP formula, in case of an absorption system, the refrigerating effect, there is no change in the numerator compared to the vapor compression. In the vapor compression system, the denominator is work of compression, here there is no compressor, here it is generator heat input. There is a device which is called solution pump which consumes little bit of this one, but in the theoretical analysis can be neglected because the power when you compare the power consumption by this pump with the compressor, it is very small. Of course, we can have the COP this also, like COP is equal to refrigerating effect divided by heat supplied to the generator plus power required to drive the pump. Here I have written the COP formula neglecting the pump work. This is neglecting pump work, neglecting pump work, neglecting the pump work. So, now this solution is heated by the solution by the returning solution. So, T5 will be less than T4, and why I have used this pressure reducing valve? Because generator is at high pressure. So, this we know the liquid will flow from high pressure region to low pressure region naturally. So, no need to have any device. So, this returning weak solution, before if the absorber has to absorb this solution, then the pressure has to be reduced. So, that is why a pressure reducing valve is used between the solution heat exchanger and the absorber for the returning solution. Now, this solution which is heated, strong solution which is heated, enters the generator, where it continues to boil. At one stage the solution contains ammonia, 35% ammonia, 65% water, this solution, and the returning solution contains 25% ammonia, 75% water. These numbers are just for making the students to understand easily. Okay. However, the concentration of solution 1, 2, 3 will be more and the returning solution concentration will be less. Okay. Now, this solution is entering into the generator, external heat is provided. What kind of external heat? We can use steam or a waste heat, exhaust gases can be used, solar energy can be used. So, that is why this is called a heat operated system. We can use a heat operated system. You can use a parabolic trough collector, okay. You can use a parabolic trough collector, even a flat plate collector. If you can produce hot water at 95 degrees centigrade, that can be used as a source of heat. Now, this strong solution is entering the generator. What happens in the generator? As heating continues further from the external, here only the external heat input is provided. The heating which takes place in the solution heat exchanger, it is internally heated, it is not from external source, the heat is not provided from external source. So, now at one stage the solution which contains 35% ammonia, the concentration will be the same, concentration will remain the same. Okay. So, x1 equal to x2 equal to x3 will be equal to, there is no change in the concentration, only the temperature will change, and similarly x4 will be equal to x5 equal to x6, which will be equal to weak solution concentration. This is very, very important, this is very, very important. So, when I say 0.35, the value 0.35 remains same at 1, 2, 3. When I say 0.25, the concentration of the returning solution, it will be same at 4, 5 and 6. How this 0.35 concentration is changing into 0.25, I am going to explain now. So, as the solution is heated, at one stage, you know, if you take ammonia and water, boiling point of water we know at atmospheric condition 100 degrees centigrade, boiling point of ammonia is minus 33. So, ammonia is the low boiling point liquid. So, at one stage ammonia vapor will come out from that solution. The solution will lose some amount of ammonia in the form of vapor. That ammonia vapor is only going to the rectifier at point number 7. So, at point number 7 the concentration will be 0.85 or 0.9. That means, here it is 90% vapor, ammonia, 10% water carryover is there. I want only refrigerant vapor to go to the condenser, not absorbent vapor. If it is 85%, 0.85 means x value at 7 is 0.85 means the remaining 15% is water. So, the water is removed by the in the rectifier. It is like a distillation, it is like a distillation column. Okay. So, which removes the absorbent from the refrigerant. Okay. So, during the process heat is generated. So, that is why the arrow mark, heat is removed from this one and the pure refrigerant vapor goes here. The concentration of vapor at point number 9. So, at this is point number 7, point number 9 will be 0.99. This is 90%, this is 99%. So, this is very important. So, how the concentration is increased from 0.9 to 0.99, 90% or 99%, the water carryover is removed by the rectifier in the rectification, that is called rectification process, and that water is sent back to the generator and the purified vapor goes to the condenser. It is because the evaporator is at low pressure. Now, this portion is similar to the vapor compression cycle. In the condenser, phase change process occurs, vapor is converted into liquid, then the heat is removed, then the liquid refrigerant, here it is pure ammonia, here it is pure ammonia, here also it is pure ammonia. If this here the concentration is 0.99, here also it is 0.99, here also 0.999, here also 0.99. So, let me write it here. So, the concentration, okay, at point number 9, let me see the number, point number 9, 10, 11, 12. okay, point number 9, 10, X11 equal to X12, that is the refrigerant concentration of the refrigerant, which is equal to 99 percentage, or 0.99. So, in this example, for the example which I have taken is 35%, so here it will be 0.35, here it will be 0.25 and here it will be 0.99. Okay. Now, this liquid refrigerant will be throttled before it produces cooling in the evaporator. The low pressure refrigerant vapor, which is ammonia vapor, comes out of the evaporator and it goes to the absorber. If you see the vapor compression system, the vapor from the evaporator goes to the compressor. Here the vapor from the evaporator goes to the absorber. Now, the absorption process takes place. Now, here at X3, at 3 the concentration is 0.35. Now, this solution is further heated and some amount of ammonia has been converted into vapor form. So, the concentration of the solution will not remain the same. The solution has lost some amount of ammonia and that vapor goes to the rectifier and condenser. So, once the solution loses some amount of ammonia, that concentration will not be there, it will be less than 0.35. That is how X4, there is a change in the concentration in X4 from X3. What it can be 0.3, it can be 0.27 or it can be 0.31. The concentration at 4 is decided by the generator pressure and the generator temperature. That is what I have written here. Generator pressure, the weak solution concentration is decided by the condenser pressure and generator temperature. Condenser pressure is nothing but generator pressure, both are at same pressure. Okay. So, the X4 will be less than X3, okay, because some amount of refrigerant has been converted into vapor form and that vapor refrigerant has gone to the rectifier and to the condenser. Now, the solution is returning. So, that is how this 0.35 has become 0.25. Suppose if this is 0.4, this will be less than 0.4. If this is 0.3, this will be less than 0.3. Now, it is this one. Now, the concentration at 4, 5, 6 remains the same. So, here it is 0.25. Now, the returning weak solution, it is absorbing the ammonia vapor which has a concentration of 0.99. Here it is, the concentration is 99%, 99%, 99%, 19 at point number 10, state point 9, 10, 11, 12. So, the solution, weak solution is absorbing the vapor whose concentration is 99%. So, as it absorbs this one, heat is generated, that is why the heat has to be removed from the absorber like condenser. Okay, so, it is exothermic reaction, and when a low concentration solution is absorbing a refrigerant vapor, the refrigerant concentration again it will increase. So, if it increases from 0.25 to 0.35, again what decides that concentration 0.35? The pressure in the absorber pressure and the absorber temperature, or the evaporator pressure and the absorber temperature. So, this is the energy balance QE, the heats, the cooling provided in the evaporator and the heat input. You can see 2 arrow marks are pointed towards the heat exchanger and 3 arrow marks are pointed away from the heat exchanger. So, QE plus QG will be equal to QA plus QC plus QR in case of for the ideal condition, theoretical conditions. Okay. If you see the water lithium bromide system, there is only one difference. You will not find rectifier, no rectifier, no rectifier. It does not use a rectifier. Here the refrigerant used is water. Okay, let me underline. This is water, and this is here the refrigerant is ammonia. So, what happens is the same process, strong solution, weak solution, water vapor, water is the refrigerant, water vapor go to the condenser, it is condensed, evaporate. All the other components are same, absorber, solution pump, pressure reducing valve, solution reducing generator are all same. Here there is this is strong solution, again this is weak solution. So, this should be a vapor. Okay. So, there is no change in the water lithium bromide system compared to the ammonia water. There is only one device which is not present, that is the rectifier is not there, no rectifier in water lithium bromide system, no rectifier in water lithium bromide system, because the refrigerant which is the vapor coming, it does not contain any absorbent. Here the absorbent is lithium bromide system. Okay. So, here the energy balance is QE plus QG equal to QA plus QC, QA plus QC. So, to summarize, we have seen the alternative to vapor compression system, we have seen heat source to site power factor. So, that brings down the site COP to a new COP or a new efficiency, that is called resource efficiency. In case of an absorption system, the power consumed by the solution pump is very less compared to the power consumed by the compressor. So, if we apply the source heat source to site factor, there is not much, there is only marginal reduction in the COP. The COP of the ammonia water system is in the range 0.5 to 0.6, and water lithium bromide is slightly higher, 0.6 to 0.7. The reason why ammonia water has got less COP compared to water lithium bromide is due to rectification problem. So, with this I conclude lecture number 22. Thank you.
Hello, I am Shikha Dikshit. I teach psychology and I am with the Department of Humanities and Social Sciences at IIT Kanpur. Today I am going to talk about what is social cognition. Social cognition is a research area in psychology which explicates the various cognitive processes that people employ to understand the social world. So, essentially it is about sense making of the social world, which involves understanding other people as well as understanding oneself. Understanding others requires understanding their traits, their internal tendencies, their contextual aspects, motives, feelings, emotions, etc. So, as we can see, this is a very complex process and requires a massive amount of information processing. Even for small decisions, for simple decisions, people have to process a large amount of information. The main perspective or the approach which is used in social cognition is obviously the cognitive approach, and which is the study of mental structures and processes. The main paradigm which is used is the information processing paradigm. As far as the range of topics in social cognition is concerned, the range is very wide, from individual level sense making to collective sense making. As far as views of cognitive sense making are concerned, there are three major dominant views in social cognition: the naive scientist view, the cognitive miser view, and the motivated tactician view. The naive scientist view emerged from research done in causal attribution, and this refers to detailed and systematic processing of information and sense making in the social world. However, it is not always possible to make detailed engage in detailed cognitive processing, and hence people act as cognitive misers in many situations. So, whenever there is lack of time and cognitive effort is less, then people involve in using certain strategies which are functional, yet they are like mental shortcuts. So, this is the cognitive miser approach. However, the question that comes to the fore is that which one of the two strategies is more important? The answer is provided by the motivated tactician view. And according to this view, people can either use the naive scientist approach or the cognitive miser approach as and when required, and they can switch over between the two approaches when required. So, these are the three major views which are utilized to understand cognitive sense making. The topics that social cognition covers ranges from cognitive social cognition to social cognition. So, topics such as causal attribution, understanding of attitudes, social schemas, unconscious cognition about social situations, the use of mental shortcuts or heuristics in decision making, social identity and stereotyping processes are some of the topics. In addition to this, a large number of social cognitive psychologists also understand collective sense making in terms of social representations.